Hello, I'm going to talk about a joint work with Itai Dinur and Keller. Roughly speaking, we show that a well-known algorithm called decay tree algorithm is optimal. The basic problem we consider is the k-sum problem. Here we are given R numbers, and we need to find k of them which sum up to 0. Up to small improvements, the best solution we know to this problem uses the technique of meet in the middle. We take all k/2 subsets of our set of numbers and find two such subsets whose sum is the negation of each other using a hash table, for example. So overall, if we take the reunion, we end up with k numbers whose sum is 0. This solution has time complexity of r to the power of k/2 sealed up. It is conjectured that this is the best solution we can have for this problem up to small improvements. So let us consider a slightly more delicate question in which we have a chance to solve the problem faster. Here we are given r integers in the range from -n to n, and we need to find k of them which sum up to 0. So is meet in the middle still the optimal algorithm for this problem? The answer is no. If n is sufficiently small, we can solve the problem in roughly O of n time using the fast Fourier transform. So overall, if n is small, meet in the middle is not optimal. Okay, this is one solution, but can we have a faster solution to this problem? So if you consider the slightly more delicate question in which we are given r random integers in the range from -n to n, then there is a famous algorithm due to Wagner, which indeed solves the problem faster. So if n is of the order of r to the power of log 2 of k, then we can solve the problem in linear time in the input size. So this gives a substantial improvement over the other solutions. I just want to mention that the Wagner's algorithm has found many applications. For example, it found applications in state-of-the-art cryptanalysis of cryptographic primitives. Also, it finds application in algorithmic problems such as subset sum problems and of decoding random linear codes. And hence, it is important to understand the Wagner's algorithm and its limitations. So let us consider a concrete problem. So suppose we have the four sum problems with r random integers in the range from -r³ to r³. So the meet in the middle approach will take us roughly r² time. The FFT approach will take us r³ time, and Wagner's four-tree algorithm is going to only take linear time, O of r. So how does it proceed? So first we sort the numbers in linear time using radix sort, for example. And then we find all pairs of numbers whose sum is smaller in absolute values than r². Now we expect to find about r such pairs because the numbers are uniformly distributed and are random. So we expect them to be about uniformly spaced. So each number is going to have an approximate negative so that their sum is going to be about r² in absolute value. Okay, now we have about r numbers of the order of r². So by the birthday paradox principle, we are going to have two such numbers which are the negation of each other. So just find these two pairs and combine them and we get four numbers which sum up to 0. So this is a linear time algorithm. And the observation which allowed us to get such an improvement over the previous solutions is that we have many solutions to the problem. So we had r to the power of 4 quadruples, and each such quadruple had a probability of about 1 over n to end up with a sum equal to 0. So we have r to the power of 4 divided by n solutions, and we need only one. So we may aim to find the solution which is most convenient to us to find. And this is exactly what we did. If we consider the four-sum problem with a general bound n on the numbers, the time complexity of Wagner's 4-tree algorithm is going to be n over r squared. And the conclusion from this is that the 4-tree algorithm is faster than meet in the middle if n is smaller than r to the power of 4, because meet in the middle took r squared time. So if n is smaller than r to the power of k, then Wagner's algorithm is better than meet in the middle. Now, what happens if n is larger than r to the power of k? So now our observation fails and only a few solutions to the problem are present. And accordingly, it is conjectured that we cannot solve this problem faster than meet in the middle. So this is a stronger variant of the k-sum problem, which says that if n equals to r to the power of k, and the numbers are randomly and uniformly distributed in minus n to n, then the best solution to k-sum problem is meet in the middle. So overall, the conclusion is that we have an answer for the question we started with. Meet in the middle is not optimal if and only if n is smaller than r to the power of k, because then we have Wagner's algorithm. But if n is larger, then meet in the middle is the best we know. Okay, so what is the next natural question we may ask ourselves? So we have a better solution than meet in the middle. The natural question is whether this new algorithm is the best we can do. I want to present two partial answers to this question. The first of them is the topic of this talk. So the first result is that Wagner's algorithm, K-tree algorithm, is optimal if k equals to 3, 4, or 5, if k is small. This optimality result relies on the random k-sum conjecture. It is important to assume the random k-sum conjecture, because even if we take n to be exactly equals to r to the power of k, then the problem of whether we can improve meet in the middle or not, important open problem. But if we assume that we cannot improve the k-sum problem where n equals to r to the power of k, then Wagner's algorithm is also optimal for general n. Also, if k is larger than 5, then also Wagner's algorithm is optimal if n is sufficiently large. If n is larger than r to the power of 3/4 of k, then Wagner's algorithm is also optimal. This is the first partial answer to this question: when is Wagner's algorithm is optimal? And the second answer was given by Zvika Brekersky and others, who showed that the Wagner's algorithm is optimal up to O of 1 in the exponent of the time complexity if n is somewhat small, if n is smaller than r to the power of log k. And we also assume that k is somewhat large. So in a sense, these two answers are the opposite of each other. In the first, we assume that k is small or n is big, and in the second answer, we assume that k is large and n is small. In the second solution, they base the optimality of Wagner's algorithm on the hardness of a worst case problem in lattices, a variant of the shortest vector problem. Okay, so now let us discuss how to show that Wagner's algorithm is optimal. So this is the exact theorem we prove. Let n small be smaller than n big. Suppose that the k-sum problem on numbers which are of size n big cannot be solved in time t. Then the k-sum problem with numbers bounded by n small cannot be solved in time t times n small divided by n big. So in general, if the big problem cannot be solved fast, then the smaller problem cannot be solved much faster. This is the theorem. And how does it imply that Wagner's algorithm is optimal? So assuming the four-sum conjecture, we cannot solve a four-sum problem with numbers bounded by r to the power 4 in time much faster than r squared, because meet in the middle is optimal in this regime. Then, using the theorem, we see that the four-sum problem with numbers bounded by n cannot be solved in time t times n divided by r to the power of 4. And if you compute it, this time is n divided by r squared. So because Wagner's algorithm has a matching running time, which is n divided by r squared, we deduce that Wagner's algorithm is optimal, assuming the random four-sum conjecture, of course. So how are we going to prove our theorem? We are going to prove the contrapositive of it. We are going to show that we can build a big solver using many oracle calls to the smaller solver. So if the larger problem cannot be solved fast, then the smaller problem cannot be solved much faster. How are we going to build a big solver using this small solver? So given input to our big problem, we are going to hash it down to get smaller numbers so that we can feed them to the smaller solver. The numbers should be of the order of n small and not n big. Then we apply the smaller solver on this hash of the input to get a tuple. And we hope that this tuple is going to be the solution to the big problem. So if every replication of the smaller solver has some chance to solve the bigger problem, if we apply this smaller solver many times, we expect to solve the larger problem. This is the idea. And the main challenge in this scheme is that we need to trick the inner solver to think that all the problems we give it are independent, so that each iteration will have an independent probability to solve the problem again. Here is a concrete suggestion for our hash. So suppose the input to our bigger problem is x1 up to xr, which are numbers which are in the range from minus n big to n big. And we are going to shrink it. We are going to look at these numbers with lower resolution. So we are going to define y to be x times n small divided by n big, and we round this result. And now we end up with a number in the range from minus n small to n small. Then when we apply the smaller solver on the on the hash of our input, then we get a quadruple, a sum of y's that equals to 0. How are we going to leverage this smaller solution to the solution to the large problem? So if we consider the quadruple in the x's that correspond to the quadruple that our solver found, then the sum of these x's is going to be small, because if we look at the numbers with low resolution, then the sum is 0. So if we again consider the full resolution, then the sum of the x's is going to be of the order of n big divided by n small. Now, because this sum is still random and is of the order of n big divided by n small, it has a probability of about n small divided by n big to be 0. So indeed, each iteration has a probability of about n small divided by n big to give us a solution to the big problem. However, this exact hash is not useful for us because if, for example, the inner solver would be deterministic, we are going to get the same quadruple over and over again, and we are going to check that a specific quadruple of x, their sum is going to be 0, and answer is going to be no, and no, and no, and no, again, again, and again. And we are not going to solve the large problem. So we need that all our attempts will be independent. So how does the true hash that we use works? So we are going to start by randomly permuting our input numbers. Then we are going to choose two random invertible elements, alpha and beta. And we are going to map x to x times alpha, reduced modulo n big. Then we are going to lower the resolution of the result. And then we are going to multiply the result by beta and reduce the result modulo n small. So this is the hash, and what are the important features of this hash that are useful for the proof? First, this hash is almost linear, and this property is important so that we can leverage the fact that the sum of y equals to 0, that the sum of x of the corresponding x's is likely also to be 0. And this is where we need linearity. Also, this hash randomizes the order of the input. And the last important property is that this hash is almost two-wise independent, so that each two elements are going to be almost independent. It is interesting whether there exists a simpler hash than this that also have these properties. I do not know the answer. The main technical lemma we use in order to prove that indeed the applications of the inner solver are independent of each other is the following. We call it the obfuscation lemma. It says that no matter what small solver we are given to the inner problem, then if we apply it on two different hashings of the same input to our big problem, we are going to bet two different solutions to the problem with overwhelmingly high probability. So no matter how structured our small solver is, if we apply it on hashing of the big input, then it is essentially almost as the inner solver gives us a uniformly random input, uniformly random solution to our problem. The way we are using the obfuscation lemma to show that the big solver we constructed solves the problem we were given is that every two solutions we get by the smaller solver are different, and each solution has independent probability to solve the big problem, and because of this independence, two-wise independence, we indeed can show that the big problem is solved with good probability. A few highlights about the proof of the obfuscation lemma, which is the main technical theorem in our proof, is that it uses discrete Fourier analysis, and it starts by reducing the problem to assuming that n big is p times q, where p and q primes, and where n small is the prime number 2. This is important so that we have many invertible elements in our group. Then we phrase our obfuscation lemma as bounding the covariance between f of x and f of y, where f is roughly speaking the small solver, and x and y are two hashings of the same big problem. And this phrasing is especially convenient to discrete Fourier analysis technique. Then what we do is to compute the eigenvalues of the noise graph given by the x and y graph. And finally, we use anti-chain arguments from Littlewood-Offord theory to bound the component of f, which is associated with the large eigenvalues of the noise graph.